Hello, it's Stat135, Lecture 17. Last time we did section 9.4, the generalized linear ratio test. Today we're going to do section 11.2, 1 and 2 sample Z and T test. This material is not covered on the midterm. So let's start with comparing two independent samples. So we have two boxes containing normal with known sigma squared and different means. So mu x and mu y can possibly be different. And we're drawing n with replacement from one box and m with replacement from the other, and forming the sample mean. Then we take the difference of the sample means, and this is normally distributed since it's a linear combination of independent normals with the following mean and variance. And if sigma squared is known, then we get this 101 minus alpha percent CI for the difference of the population means. If sigma squared is not known, then we have to find an unbiased estimator, and we're going to use the pooled sample variance because it will allow us to do a t-test as we see below. So the pooled sample variance is given in this formula here, and you can check that it is an unbiased estimator. And it has nice properties that if x1 to xn is IID normal, y1 to yn is IID normal, same variance, sigma squared, then the test statistic shown here has a t distribution. So let's see why. So let's recall first what a t distribution is. So it's a ratio of independent normal and chi squared. And so here what we have is, let's also recall that n minus 1 sample variance over sigma squared is a chi squared with n minus 1 degrees of freedom. So that so now we have two chi squares that are independent of one another because x and y are independent here, and so these chi squareds add and gives us a chi squared with n plus m minus 2 degrees of freedom. So now let's define z as shown here. It's easy to see this is standard normal, and let's define u as defined here. Easy to see that this is chi squared with n plus m minus 2 degrees of freedom. So then z over the square root of u over n plus m minus 2 is a t distribution. Just to verify that, the reason that z and u are independent is because the sample mean and the sample variance are independent for x and y, and that's something we mentioned in lecture 8 on page 5 if you want to review that now. So it remains just to show that that what we have z over the square root of u over n plus m minus 2 is our test statistic. So I just do some algebra here. It's pretty straightforward, and that's it. So now from theorem A, we can write that the standard error, I'll denote that as s x bar minus y bar, is the square root of the pooled variance times 1 over n plus 1 over m. So then we have a corollary that for sigma squared not known, a 101 minus alpha percent CI is given here, and notice that this involves a t distribution. Great. So now let's do hypothesis testing for a two-sample problem using the t-test. So we can have a two-sided alternative or a one-sided alternative, but our null is that the sample means are the same, so their difference is 0. I mean, the population means are the same. So for alpha level of significance, so the test statistic used to make a decision whether to reject the null, assuming the null is true, is x bar minus y bar minus, now the difference of the population means is 0, so we subtract 0 divided by the standard error. From theorem A, we know this is a t-distribution, and so we have our rejection region here, and our two-sided alternative. For a two-sided alternative, we reject the null if our test statistic is, the absolute value of our test statistic is greater than our cutoff, t n plus m minus 2 degrees of freedom alpha over 2. Or equivalently, you can say that 0 is not in the 101 minus alpha % confidence interval. Those two statements are equivalent by the duality of hypothesis testing and confidence intervals that we saw last time. So also note that if n and m are large, that the t-test is approximately a z-test. Remember that the t-distribution asymptotically approaches the z-distribution when the degrees of freedom approaches infinity. So, and also note that the t and the z-test, where did these things come from? So they actually are equivalent to a generalized linear ratio test. I'm not going to prove that, but it's in your book, and you should take a look at that on page 426 to see where did this z and t test come from. So it's just coming from a generalized linear ratio test from chapter 9. So then we finally did this problem, which is actually a one-sample z-test. So we just have one population here that we're looking at, which are men's weekly earnings. And our null hypothesis is that men weekly earnings is 670, which is women's weekly earnings. And the alternative is that men make more than women. In other words, mu is greater than 670. We have alpha is 0.01, and the sample mean is 725, and S is 102, and N is 40. So we can calculate our test statistic. We're told that we can just approximate the z test as a z test here. So here we go. So we find the test statistic 3.41, which sounds kind of large, and indeed it is. So our rejection region is greater than 2.326, so we would reject. Or you can find the p-value. I should have written here, this is the CDF. So the p-value indeed is less than alpha 0.01, so we reject the null. So that's the show for today. I'll see you next time.